In this session, we're going to talk about the idea and definition of chirality. We're going to talk about chiral centers, the number of stereoisomers that are theoretically possible, which is a function of how many chiral centers there are, how to identify a molecule as being chiral or achiral, and the concept of enantiomers. And for this activity, it'll be helpful to have two models of 2-butanol, which has this structural formula. And it's going to be most useful if we just put together the basic carbon chain and put a hydrogen only on the new number 2 carbon, and if you want to, on the OH group. And that will take a few minutes if you want to make your model. And it should look something like this. So we've got 4 carbons in a row, we've got a hydrogen and an OH group on the number 2 carbon. Now, chirality in general is the idea of handedness, or specifically the property of having a non-superimposable mirror image. And we say handedness because when we have two hands, we have two objects that are very similar, and we'd say they're more different, or they're more similar than constitutional isomers, right? If you picture the fingers as substituents, we've got pinky finger, ring finger, traffic finger, nose finger, and thumb on each hand, and they're all in the same order. And yet the two hands are different, right? And we'd say they are non-superimposable, which means that we can't put one on top of the other and have everything match up. Now we can if we go palm to palm, but then we're not really superimposing one on the other. We're actually having them mirror one another. And that's because although the fingers all line up, the palms are face to face, whereas superimposing would mean they'd have to literally be on top of each other and pointed the same direction. So we'll talk about that term, and we'll use that term, the idea of being superimposable or non-superimposable, a lot in this section, and so it's something that we want to think carefully about. Now, if we drop to the molecular level, we'll line up our butanol molecule here. If you build a second model of 2-butanol, you're going to find that one of two things happen. Either you build a second one that's identical to the first one, and superimposability would be to literally be able to pick up one and set it down on top of the other so that everything matched. Notice here that the carbon chain is perfectly lined up, the number 2 carbons are on top of each other, the hydrogens match, the OHs match, the methyls or CH3s match, and the CH2 CH3s match. Or you may have built the mirror image. And so this is a model of the mirror image of 2-butanol, of the first one that we built. And notice that the mirror would be right here. So everything mirrors. So they are mirror images of each other. And there's a number of different ways you can visualize that. You could imagine looking at each other in the mirror. But they are non-superimposable. If you put one on top of the other, we can get the carbon chains to align, but then the OH of one matches up with the H of the other, and vice versa. We can get the OH and the H to match, like this so. OH is up here, H is here, but then the carbon chains are misaligned. A CH3 on one is at the same position as the CH2 on the other. And so these molecules are clearly different, but yet they have the same, not just constitution, well, they have the same constitution, right? They have same formula, but same connectivity as well, and that OH group is on the number 2 carbon on both of them. But they're not the same. And that means that they're both chiral, and it also means that because they are non-superimposable mirror images, that they are both chiral and they are enantiomers of each other. And enantiomers, by definition, are non-superimposable mirror images. And an object is chiral if it has an enantiomer, or if its mirror image is different. Now, everything has a mirror image, except vampires, but the mirror image of some molecules is the same. For example, if we take the hydrogen off and we just put the OH at the end, now we have one butanol. We can arrange them in different ways, right? But we'll always be able to adjust the conformation of one so that it overlaps the other. And if we switch the OH to another position on that same carbon, we can still twist it around so that they align. And by the way, if we went back to our original pair of butanol molecules, two butanols that is, I want to point one thing out here, which is that the carbon where they were matching or mismatching is the number 2 carbon, and it has 4 different groups attached. There's a CH3, a hydrogen, an ethyl group, and an OH group. And so that makes it a chiral center. And there are 2 different possible ways that those 4 groups could be attached around that carbon. And we'll later start referring to them as the absolute configurations R and S. But for now, we just want to realize that when we have one of these chiral centers, which is a stereo center, or a position where stereochemistry happens, that we have 2 options, right? So that allows us to figure out the number of possible stereoisomers. And again, if we just recap, a chiral center is going to be an atom. For us, it's almost always going to be a carbon with 4 different groups. The number of stereoisomers possible is going to be 2 to power of n, where n is the number of chiral centers. Or let's say stereocenters. Because later we're going to find out that there is another type of stereocenter that's not a chiral center. And so a chiral center, again, atom with 4 different groups, is a type of stereocenter. So if we have, for example, this molecule, and we frequently put an asterisk on the chiral carbon, with 1 chiral carbon, then we have 2 possible isomers. And again, to identify whether a molecule is chiral or achiral, we want to look at its mirror image. And if the mirror image is different or non-superimposable, then that object is chiral, and the mirror image is its enantiomer. So again, to be chiral, you have to have an enantiomer, which is a mirror image that's different or non-superimposable. You can't put one on top of the other. And by the way, let's take a quick moment to see how we would draw these in a wedge dash configuration, and then we'll look at some examples. So if we want to draw, let's say, this particular enantiomer, one way to do it is to use a wedge dash type of drawing. And the easier way to do that is going to be to use the longest continual chain flat on the page, And then to include the groups, notice that the OH is sticking out at you and the hydrogen's in the back. So wedge is out, dash is back, and we'd put those groups like so. So let's use this pentose, or 5-carbon sugar, as an example. See if you can find all the chiral centers and then figure out the number of possible isomers. Now, in locating a chiral center, we're looking for a carbon that has 4 different groups attached. So we can automatically rule out any carbon like this CH2 group at the end that has 2 hydrogens. Because if you have 2 of the same thing and you only have 4 things, you can't have 4 different things. We can also rule out the oxygens, which only have 2 things attached. And lastly, we can rule out this trigonal planar carbon that has the double bond because it only has 3 groups also, which means you can't have 4 different ones. However, we'll see that this carbon has a hydrogen, an OH, it has a CH2OH, and then it has a CH, and the rest of the molecule here. So that's 4 different groups. This carbon likewise has the aldehyde, or C double bond O with a hydrogen. It has an OH, it has a hydrogen, and then it has the rest of the molecule. As it turns out, this carbon has a hydrogen and an OH, is also chiral, and even though there's a CHOH on both sides, for the groups to be identical, they would have to be identical all the way through the end of the chain. And in this case, we go this direction, we've got the CHOH, but then we have a CH2OH. In this direction, we have the CHOH, but then we have a C double bond OH. And so those 2 things are different, which makes that chiral, or that carbon in the center, chiral. And now with 3 chiral centers, we'd have 2 to the 3rd possible stereoisomers, and that would be 8 possible stereoisomers. And just to help us draw a few, let's come back to this idea of the chiral center having 4 different groups, and let's imagine that each of those chiral centers will keep the chain, starting with this OH, moving all along the chain to the double bond O. We'll keep that in the plane of the page, and let's just randomly pick a group on each carbon, each chiral center to be pointed towards us. So one option would be to have all the OHs wedged, which would mean all of the hydrogens were dashed. Right? The enantiomer, or mirror image of this, by the way, would be exactly the opposite. So it would be all the OHs dashed. And while that's not easy to visualize in this, with it drawn like this, you could draw it or build the models and play around with them some and see that that is in fact the case. The way to look at it and visualize that drawn the way they are would be imagining picking one of these up, lifting it up above the plane of the board or the screen that you're watching, and slide it over to the other. So it's as if you're looking in the mirror with the molecule, where all the OHs of the top one are pointed towards us, towards the screen. It's as if it's behind the screen, looking at us, and the OHs of the other one, the one that's closer to us, are pointed away from us or towards the screen. Right? It's kind of like when you look in the mirror, if the OH is your nose is close to the glass, your mirror image's nose is close to the glass as well. So we could think of this as a wedge, wedge, wedge option, and this is a dash, dash, dash. right? And those are only two of a number of possibilities. The other ones, by the way, would be dash, wedge, 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 dash, wedge, 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 dash. Then we could also have two dashes, dash, dash, wedge, dash, wedge, dash, and wedge, dash, dash. And that is our 8 theoretical possibilities. And it turns out all of those compounds exist, and they are the aldopentoses, or pentoses, which are sugars with 5 carbons. And these are all sugars that exist.